Okay, so hello everyone again. This is lecture 6 part 3 of wave optics. In this lecture I will continue our discussion on diffraction concept. So I am Sameer Lavankar. Let's move on with our discussion. So course outline for you, we started with the introduction concept, that is of wave optics. Why is there a difference between a wave theory and a Descartes theory, that is particle theory of light. Then in Hume's principle we understood the concept of wavefront, followed by the refraction and the reflection laws being explained using Hume's principle. We proved the complete concept of refraction and the reflection laws of light using Hume's principle and wavefront concept. Moving on to the coherent and incoherent addition of waves, why was there a difference in the intensities being maximum for coherent and minimum for incoherent. Similarly, we also understood a small concept of Doppler effect in this concept only. Moving on to the interference of light rays and Young's experiment. Why was there a need of phase locking for the interference fringes to happen? What is the fringe width? What is the simple scenario? What is the different criteria being observed? What will happen in the on the effect of fringe width if there is a change in the monochromatic source of light to a complete white source of light? Why was constructive interference happening at some distance x known as n lambda capital D by small d? Why is destructive interference happening at some n plus 1 by 2 lambda capital D by small d, etc. So this was the complete concept of interference of light waves and Young's experiment. Right now I am trying to explain you the concept of diffraction. What is diffraction? Diffraction is nothing but the bending of light. It is a phenomena in which the light bends. Why does it bend? It bends through the corners. What is the responsible criteria for it? The responsible criteria is that the wavelength of light should be in the order same as that of the obstacle through which it passes through. So let us move on through our discussion of diffraction here, and then finally after the completion of diffraction we will move on to the final concept called as polarization. So this was being explained in the last class only. For this lecture let us move on to the single slit experiment being done. So in the discussion of Young's experiment we stated that a single narrow slit acts as a new source from which light spreads out. So here this source of light acts as a new source through which the light spreads out. So even before Young many did the same experiments such as Newton, etc. So even before Young, early experimenters including Newton had noticed that light spreads out from a narrow hole or slit. It seems to turn around corners. So please look over this. It seems to turn around corners and enter regions where we would expect a shadow. So sometime, as we also explained in the last concept, that there was a portion between the two slits where the shadow should have been explained, but because there was a light being formed even at that shadow position, so it was being explained that it can't be explained during the Descartes theory of light. A wave theory needed to be used to explain this theory. So these effects known as diffraction can only be properly understood using wave ideas. So these effects known as diffraction, this is nothing but an effect known as diffraction, can only be properly understood using wave ideas. When the double slit in Young's experiment is replaced by a single narrow slit. So please make sure now there is a change in the design criteria here. So when the double slit in Young's experiment is replaced by a single narrow slit illuminated by a monochromatic source, a broad pattern, please make sure it is a broad pattern here, a broad pattern, this is a broad pattern, let me write here. So it is a broad pattern being explained. So a broad pattern with a central bright region is seen, a broad pattern with a central bright region is seen. On both sides there are alternate dark and bright regions. So a bright pattern with a central bright region is seen. On both sides there are alternate dark and bright regions, the intensity becoming weaker away from the center. Quite evident, I explained in the last lecture also that as you move away, as the path difference keeps on increasing, then the value of intensity keeps on decreasing. So as you can see the intensity is being decreasing in this sense. Also as you can see it is a bright fringe here, then it is followed by a dark fringe here, followed by again a bright fringe here and then a dark fringe here. So this is one of the explanation I need to convey to you. Now why does it happen? I will try to explain you in the subsequent slides for now. So this thing is also explained, this thing is also explained. Let us move on to the next point. Also one thing to notice here is we are using the source of light to be a monochromatic source. No dichromatic source, no complete white source of light, a monochromatic source is being used. What does it mean by a monochromatic source? Monochromatic source means a light which has a single wavelength. Okay. So to understand this, go to the below figure. This is the below figure being talked about here. Go to the below figure which shows a parallel beam of light falling normally on a single slit Ln of width A. So now please look over this carefully because very small mathematical formulations are to be used, some trigonometry should be applied and then this thing can be explained quite evidently. So here what does it try to say is that let us say this distance is ln, which is saying width a. So this is the complete width size here. So to understand this, go to the below figure which shows a parallel beam of light falling normally on a single slit ln of width a. So this is that parallel beam of light, parallel beam of light which is falling on this width a. The diffracted light goes on to meter screen. So after this, diffraction happens even from this portion or this portion, from this portion, like this or like this. So it happens and then it goes to the screen. Where is the screen? Screen is somewhat kept here. The midpoint of the slit is M. So it is just a simple denotion. It is denoting the midpoint of the slit be M. Then a straight line through M perpendicular to the slit plane meets the screen at C. So a perpendicular is being talked. So this is that perpendicular being talked about. This goes and it reaches a point C which is at the screen. So a straight line through M perpendicular to the slit plane meets the screen at C. So this is being explained, this is being explained, this is being explained. Now we want the intensity at any point P on the screen. So we need to just find out the value. Let us say this is at point P we need to talk about. It is at a distance x from this point C. We just need to find out the intensity, what is the intensity at that point. So now we want the intensity at any point P on the screen. As before, straight lines joining P to the different points L, M, N, etc. can be treated as parallel, making an angle theta with a normal MC. So here one of the assumption which we need, that this small a is very less than this capital D. What is capital D? Capital D is this distance. So because this distance is very large, let us say this is that point P being talked about. If we are just seeing in this portion, then these lines, these set of lines can be understood as parallel lines here at this point. At lower portion it will reach P, but for this point we can assume it that these are parallel lines. So making an angle theta with a normal MC. So here this angle is denoted by theta here for you. Then the basic idea. So now for finding out the value of dark fringe or central fringe being formed, one of the idea which we are performing is the basic idea to divide the slit into much smaller parts and add their contributions at P with the proper phase differences. Next is we are treating different parts of the wavefront at the slit as secondary sources. So this is one of the assumption also, that we are treating different parts of the wavefront at the slit as single secondary sources. So now what happens, why there is a decrease, we will try to explain it from this slide here. So now because the incoming wavefront is parallel to the plane of the slit, these sources are in phase. Quite evident, because there is only a single source of light, only a single slit was being kept, and then there was a interference fringe being formed on the screen. Therefore it is the sources are in phase. Why is it in phase? Because the phases are being locked. Why it is locked? Because it is using a single source of light. So because the incoming wavefront is parallel to the plane of the slit, these sources are in phase. So because these are parallel here, therefore the sources are in phase. The path difference NP minus LP. So now the path difference to be asked is, this is, let us say this is that NP being talked, this is the LP being talked. Because we are assuming both to be parallel, therefore we can just superimpose this portion into this portion here, and then we can find out that the path difference is nothing but this distance NQ. So finally the path difference will be nothing but, after the superimposition of this point this line onto this line, we will find out the value. So this can be deducted directly, and whatever which remaining is nothing but NQ here. So the path difference NP minus LP between the two edges of the slit can be calculated exactly as for Young's experiment. So from the figure, NP minus LP. So NP, this, let us say this is N, this is P, minus LP is nothing but NQ. So I explained you why it is NQ here, which is equal to A sin theta. So how does this A sin theta came? I will try to explain you here. So let us suppose this is a triangle being formed. This is the L, this is this Q, this is this N. Now if this angle is theta, from basic trigonometric concept we can find out that this angle is also theta. Now if we have this value as A here, then this value will be A cos theta and this will be A sin theta. So this is simple mathematical calculation, nothing very terrific into this. And we also know that if this value theta is very small, why it is being assumed as small? Because we assumed the first concept as small a is very less than capital D. So because the distance of the screen is very far apart, therefore we can understand that this theta formed will be very small, and if it is very small, then that means that the value of sin theta can be assumed equal to theta. Therefore, and please make sure that here theta is written in radians. So therefore, sin theta is approximately equal to e theta. So what do we understood from this portion, that if we have this slit distance as a, or if we denote the slit distance as any point a, b, c, d, e, f, then only multiplying that value by theta gives you the path difference from the two corners of the position. So this is that new concept which we found out, that NP minus LP, that is path difference, is equal to a theta. Similarly, if two points m1 and m2 in the slit plane are separated by y, so now we are assuming some points m1 and m2. Here this m1 and m2 will be this. So for us, let us suppose that this is y. So the path difference is nothing but m2p minus m1p equal to y theta. So this is the similar case only, that for any slit difference being observed, we just, if we need to find out the path difference for it, it will be nothing but that multiplied with the theta value. What is that theta value? Theta value is nothing but the a angle subtended from the corners to that point P, either from the above portion or from the below portion. Therefore, for m1 also, because we are assuming that every line which is passing through that point to the point P assumed as parallel, therefore the angle subtended by each point will also be same. Because the angle subtended by each point will be same, therefore the value of theta will be same for any point which is lying between L and N. Therefore for m1 and m2 also the value of theta will be same, and similarly if we need to calculate the value of path difference for between m1 and m2, as the difference between m1 and m2 was y, therefore the value of path difference is y into theta. So therefore we found out this value as m2p minus m1p is approximately equal to y theta. So this is being explained, this is being explained. Now we have to sum up equal coherent contributions from a large number of sources, each with a different phase. This calculation was made by Fresnel using integral calculus, so we omit it here. So now finally what we need to do is, we just need to find out at which point this value is equal to lambda by 2. So for those points, if we found out that the value is lambda by 2, then destructive interference is happening. If the destructive interference is happening, we know that the value of lambda intensity is 0. So for that portion we will just deduct that, and the portion which is left will only applicable for the interference fringes to form on the screen. Okay, so this theory is simple. From this slide we just understood that the value of the path difference for any 2 points will be nothing but that distance multiplied by theta. So next point, now the main features of the diffraction pattern can be understood by simple arguments. So now at the central point C on the screen, the angle theta is 0. So quite evident that if we try to make these parallel lines here, then the value of theta will be 0. If the value of theta is 0, the path difference will be 0. If the path difference is 0, there is maximum intensity. So at the central point C on the screen, the angle theta is 0. All path differences are 0, quite evident, and hence all parts of the slit contribute in phase, quite evident. This gives the maximum intensity at C. Therefore we will find the maximum intensity at C. But now what happens when we try to change it from point C to, let us say, some point P? Now experimental observations shown in the below figure indicate that the intensity has a central maxima at theta equal to 0 and a secondary maxima. What is secondary maxima? Any other maximum but with less intensity at theta approximately equal to n plus 1 by 2 lambda by a, and has a minima at theta approximately equal to n lambda by a. So first of all they tried to give the conclusion statement, and then in the subsequent slides I tried to explain you why it is, why for minima it is theta is approximately equal to n lambda by a. So for any distance, for any theta at which the value is equal to n lambda by a, what is the lambda? Lambda is the wavelength of this monochromatic source of light. What is a here? A is nothing but the slit difference, slit width. So now why it has a minima, let us try to explain it from the subsequent slides. So now it is easy to see why it has a minima at these values of angle. So now let us move on to next slide now. So consider first the angle theta where the path difference a theta is lambda. So now this is one of the assumption. We are assuming a point at which this path difference is nothing but lambda. We are using that angle. Let us say we try to subtend, and at one point we found out that value of a theta is equal to lambda. Then simple calculation. So theta is approximately equal to lambda by a, quite evident. Now divide the slit into 2 equal halves. So now this slit is divided into 2 equal halves. So one is LM, one is LN. So let me write here. So one slit will be nothing but LM, another slit will be nothing but MN. Each of size a by 2, quite evident. The size will be divided into 2, so there will be a by 2 size for every point m1 in LM. So just let us suppose we have a point anywhere between L and M, that is denoted by m1, and similarly there is a point m2 in Mn. So any point which is in Mn we are denoting by m2. The path difference such that m1 m2 is a by 2. So quite evident, if we take any point m1 here, and there we will find a value of m2 such that this distance is a by 2. Similarly, even in this portion we can find a value of m2 such that this value is a by 2. Similarly, if we need to calculate at some center point, let us say at this portion, we will find a value of m2 such that this value is a by 2. So, we can find infinite values of m1 m2 at which value of distance m1 m2 is equal to a by 2. So, after this successful determination, the path difference between m1 and m2 will be, so let us say I need to calculate the value of path difference from m2p minus m1p. So, that will be nothing but as we know the slit difference between this is nothing but a by 2. So, a by 2 multiplied by theta will be the slit which we calculated in the last concept. So, theta a by 2. Now, we know that theta is nothing but lambda by a. So, therefore, we will get the path difference. Let me write path difference as PD, which is equal to theta into a by 2. Let me write theta is lambda by a, so it will be lambda by a into a by 2, which is equal to lambda by 2. So, we found out the value of path difference is equal to lambda by 2. Now, in our previous concepts of incoherent addition of waves and coherent addition of waves, we understood that for destructive interference to occur, the value of path difference will be lambda by 2. Hence, what we found out that for any point, if we take it as single sources, for any point m1 between L and M, there will be a point m2 which will be destructive, which will try to destroy its intensity pattern, which will try to destroy its intensity pattern. Therefore, for the complete slit A width, we can't find any intensity, hence it will be a dark fringe. So, this means that the contributions from m1 and m2 are 180 degree out of phase, quite evident as the value of destructive interference lambda by 2 is occurring here, and cancel in the direction that is theta is equal to lambda by a. Contribution from two halves of the slit Lm and Mn therefore cancel each other. So, because it cancel each other, hence at any point which is theta, if that theta is approximately equal to lambda by a, then at those points we will find out no intensity being happening. Hence, at those points the value of intensity will be 0, therefore dark fringes are observed there. So, this is the concept of minima. The concept of maxima I will try to explain in the next class. So, for now let me try to summarize the complete situation here only. So, in this lecture I started with the single slit experiment. So, single slit experiment is nothing but a monochromatic source of light occurring on a single slit. After this single slit there is a diffraction being occurring, and due to this diffraction there is a central bright fringe happening here, followed by dark fringes and white fringes, but only intensity pattern is being changed. The intensity pattern changes as in the value of intensity keeps on decreasing as we move away. Why does it move away? Why is there a difference in the intensity pattern as we move away? I will try to explain, but for now in this lecture I explained to you why is minima occurring only and only when theta is approximately equal to n lambda by. So, for any value of n lambda by, as we know that the destructive interference happens when the path difference is n lambda by 2. So, for n lambda by 2 the theta is always n lambda by a. Therefore, for any theta which is a multiple of lambda by a, there will be destructive interference happening, and hence we will find out dark fringes happening in these positions. So, let me put a stop here. In the next lecture I will try to explain to you why is there a difference in the interference in both the directions. So, the course progress for you, we started with the introduction concept, then followed by the Huygens principle, then diffraction and the reflection laws are being done, coherent and incoherent addition of waves was being explained, Doppler effect was also a part of this only. Then in the last subsequent lectures, interference of light waves and Young's experiment is also being done. Today we started with a diffraction concept. This diffraction concept is being put apart. A single slit, why is there a difference in the intensity is needed to be explained, followed by a double slit experiment. What happens in a double slit experiment, what is the difference between interference and diffraction needed to be explained, and then we will go to polarization. After the successful completion of polarization, the complete wave topics concept is completed. So, let me stop it here only. Thank you.